Hello, everyone. Mr. Schultz here as we dive into our last segment on statistics, also known as 8.5 Estimating Population Parameters. Make sure you still do your end of lesson reflection as well as explain the lesson. Give me the gist in a sentence or two, one or two sentences. More than that, don't need that. Let's go on. So, vocabulary and concept review. Make an inference. A man runs after a moving bus, waving his arms frantically. So, I infer, missed his bus. He does not have time to wait. That's the inference. I think the man missed his bus and he doesn't have time to wait. That's it. So, when you make an inference, you take what do you see and you come up with an educated guess. Data from a sample can be used to make inferences. So let's write that in. Inferences about the corresponding population. So this is the basis of inferential statistics. So sampling error. So due to the variations between different samples of a population, there can be errors that are not created from biases. For example, when you went to like for example when we were thinking about asking what should our new mascot be, if you went to specifically the cat club and you thought that represented the whole student population, well, probably that would be a bias because you went to a place where most of the people probably like probably like cats. Hypothetically, you could randomly select a small portion of people that will that do not reflect the population as a whole. So what if you randomly selected the first, not the first 10, but like every 10th person, you randomly selected people asking, hey, what should our new mascot be? And every 10th person happened to be part of the cat club. Hypothetically, you didn't try to have a bias, you didn't go to the cat club, but this sampling error has occurred. So this is what we call a sampling error. Give me 1 second. So this is called a sampling error. So how can we fix this? Well, sampling errors will decrease if you increase the number in your sample. So let's say you asked 50 people, every 10th person coming into the campus. Well, if we increase that number to 100 people, every 10th person coming in, and there's 100 people in your sample size, that's going to decrease the sampling errors you may get. So, standard error of the mean. So, let's get that formula up. I'm going to copy and paste it, and then we'll discuss it. So, standard error of the mean is simply, you take the standard deviation right here. Let's circle it in blue. Here's the standard deviation, and you divide it by the square root of the sample size. That's it. Let's go on. So we have this key concept, maximum error of the estimate for a sample mean. Well, here's the formula, okay? Z is a specific value that corresponds to the confidence level. So we have to figure out what type of confidence level do we want. S is the standard deviation, and N is the sample size. So here are the three most common degrees of certainty. We're going to have 90%. So let's write this in. 90%. Oh, let's do black. We have 90%, 95%, and 99%. It's always kind of interesting how people will say, hey, we are 99% certain. Well, if that was the case, we'd have a lot of bets going down and people risking a lot of money. But there's always people who are betting against the system right there. So if we want a certain percentage, we'd use this value, z value, that corresponds to them. That's it. Let's go on. So estimate the population of the mean. Well, right here, we have to determine the degree of certainty. And then we have this maximum error, this estimate E. And then we can, subtract on both sides. The mean of the random sample, subtract by E, maximum error. We can estimate, hey, the population should be between these two things. But let's go on. So finding the maximum error of the estimate. So let's just dive in and do an example from a problem from each of the examples. We have example 1, athletes. A poll of 350 randomly selected athletes show they spent an average of 10.25 hours per week at practice with a standard deviation of 2.3 hours. Use a 95% confidence interval to find the maximum error of the estimate for the time spent practicing. Hold up. All right, so if we want 95% confidence, we want the z-score of between negative 1.960 and negative 1.960 for the other way. So we can take the formula, E is equal to Z times S divided by the square root of N. All right, well, let's plug in our data. So if we plugged in, positive, if we plugged in 1.96, we're going to find out the maximum error. And we understand that, hey, our standard deviation is 2.3. Well, how many people do we have? Well, we had 350, and so we're going to find the square root of that. And if we used our calculator, we should get a maximum error of around 0.24. So we can say with about a 90, so let's type this out. And let's go black. With a 95% confidence at the mean time an athlete practices each week is within 0.25 hour of the sample mean time. So that's what it's saying. Hey, we're 95% confident that the mean time an athlete practices is 0.24 of an hour of the sample mean time that we gathered. Let's go on. Example 2, estimate a population mean. All right, well, once again, we need to calculate E, and we're like, all right, what could E be? So we want to have a 90% confidence. So we can start off with E is equal to Z times S, and what we have, square root N, the number of people. So we understand that E is equal to, well, at 90%, it would be 1.645. And we're going to times it to, well, standard deviation was 2.7. And we're going to divide by that by, hey, sample of 200, the square root of 200. And then if we gather this up, we understand that, hey, this is going to be about, let's erase that. It should be about around 0.31. So now we can determine something else. So we understand that, hey, look, we're going to take our sample mean and we're going to subtract it by our error. But wait, we are also going to add it. So what we get is we get 5.8 pounds minus 0.31, and we're going to get 5.8 plus 0.31. So that would be 5.49 pounds and 6.11 pounds. So when we talk about this, what we would probably say is, hey, with 90% certainty, and let me type it all out and then unpause it. All right, so with 90%, the confidence interval, the population mean is between 5.49 and 6.11. Therefore, we are 90% confident that the weight of the packages will be between 5.49 and 6.11 pounds. All right, let us go to example 3 and 4. So, normal distributions. We're going to estimate the population proportion. All right, guys. So, we're going to talk about population proportion. So, the proportion of successes will equal p hat. That's just like a little p with a little chevron on top. P hat is equal to x over n, where x is the number of successes and n is the number of trials. The proportion of failures, q hat, will equal 1 minus p hat, because 100% is success and failure put together in this situation. So, a survey of 215 students at Laundry High School asked them if they ride the bus to school. 46 responded saying that they do. Use a 95% confidence level to estimate the population proportion for all 1,109 students. So, let's set it up. First we have to find the proportion of success and failure. So we have p hat is equal to x over n. And 46 said they do, whereas out of 215. So that's going to equal 0.214. That's, less than a quarter. So the q hat will equal 1 minus 0.214, also known as 0.786. So that's our p hat and our q hat, our successes and our failures. All right, so before we begin, we have to verify, hey, look, was our sample size large enough? So there's this formula right here. We take the total number of our sample and we multiply it to our successes. And we take our total number and we multiply it to our failures. So if we have 215 times 0.24214, and we have 215 times 0.786, it has to be bigger than 5 or equal to 5. And if we multiply both of these, we get 46 and 169 respectively. Well, yeah, it's bigger than 5. So we can go on and we can use the formula I'm about to give you in 3, 2, 1. All right, so here, let's write down this formula. We have the error right here will equal z times the square root of p hat q hat divided by n. So now what confidence level do we want? We want 95%. So this will equal, and now it's just like take your formula and plug and chug. You just need to plug in all your information. So our error will equal, and 95% was 1.96. So 1.96 times the square root of 0.214 times 0.786. And then we're going to divide by 215. And so we get an error right here of 0.055. So now we just need, determine our confidence interval. So this is going to be, p hat plus or minus this e right there. So our p hat plus or minus e is going to be 0.214 plus 0.055 and 0.214 minus 0.055. And so we would get 0.159 around 0.269. So what does this do? Now, this is a lot just for this right here. So that's why you should take a couple days on this. We have a 95 confidence interval that, that the P, let's write this out, that the population proportion, so is going to be between 0.159 and 0.269. So we are 95% confident. So we are 95% confident that, and I'll pause it and type it up, all right? So we are 95% confident that the proportion of students who ride the bus to school is between 15.9% and 26.9%. So this gives us like a proportion, or like, hey, what proportion does this? And then we have to figure out the error. Like we're like, all right, we want to be this confident. And then, or we are this confident in this data or something like that. And then we take that, we plug it in our formula, and then using that information, we could be like, all right, from the sample, we find this error zone, and then we're like, all right, we are 95% confident that the proportion of students are between this number and this number, or percents. All right, so let's do our final example, misleading population estimates. So an employee at a restaurant conducts a poll about the satisfaction with their lunch menu. The report claims with 80% confidence that the proportion of students or people who are satisfied with the lunch menu is between 85 and 90%. The sample size was 15. Identify any misleading representation of data. So let me write it out and then explain. All right, guys. So the sample size of this guy is 15. We know that the successful population is going to be 0.85. And we know that if we do 1 minus 0.85, we get 0.15. So we take the sample size, and we do it, times it to the successful right here. So that would be 15 times, and it was 0.85, 0.85. This would equal 13. That's good. It's above 5. So we do a little check. Now, if we do the failures here, we do 15 times 0.15. That actually equals 2. 2 does not equal 5. So the sample size is too small. So sometimes, that's just how it is. The sample size is too small, so we can't to use this confidence interval right here. In addition, the confidence level of 80% is too low. We need to go a little bit higher. You got to pump those numbers up. Okay, guys? All right, guys. Thank you for this extremely long video, but I'll catch you guys in class. Bye.